Okay, I'm happy you are still here. I'm very happy to present Sonia Rueda from Universidad Politécnica de Madrid. And here is her title.
Thank you very much for organizing this session and for giving me the chance to talk and add to this variety of topics. So first of all, let me tell you or give you a hint of what is an algebro-geometric differential operator. Well, I wanted to say that this is recent and ongoing work with María Ángeles Zurro and Juan Morales Ruiz. They are also in Madrid, and Emma Previato, who is from Boston University. So algebro-geometric ordinary differential operators can be characterized for having a non-trivial centralizer. So we are in the theory of commuting ordinary differential operators. And by one of the experts in the area, this theory has a broad connections with many branches of mathematics. First of all, to the integrability of partial differential equations, because constructing new commuting operators gives explicit solutions. Also in algebra is related with the Dismier, Jacobian, Poisson conjectures, and in complex analysis and other areas of mathematical physics. But what are our goals in this theory? What we wanted to do, our contribution is to try to have to use effective differential algebra to develop symbolic algorithms. For example, in this occasion, to factor ordinary differential operators related with spectral problems. Also computing new pairs of commuting ordinary differential operators, and overall developing a Picard-Bézier theory for spectral problems. For example, our first interest was in the Schrödinger one-dimensional Schrödinger equation, where you have a parameter, a spectral parameter lambda, and a potential U that satisfies one of the Korteweg-de Vries equations, one of the equations of the KdV hierarchy. For example, the first equation of the hierarchy is the classical KdV equation. But we want to approach this problem with the ideology of Drag, already from 1919, and is to integrate this equation as an ODE to obtain solutions that depend on X and also on the parameter lambda as a parameter. Well, these are the context of my contents of the talk. It may be a bit long, so probably I will have to jump over some things to stay in the time frame, but let's see. So first I will tell you about a bit more about on the theory of these algebra-geometric ordinary differential operators. Then the algorithm we developed to factor and which goal, which is the spectral Picard-Bézier extension in this case, and I will finish with some ongoing research. So it was already known at the beginning of the 20th century that the centralizer of an ordinary differential operator is the affine ring of a curve, which is called the spectral curve. And later, a bit later, Burnell and Chaundy established this correspondence between commuting differential operators and algebraic curves. So given an operator L, there exists another operator that commutes with it, and it's equivalent to say that these two operators satisfy the equation, an algebraic equation that defines this spectral curve, the algebraic curve. And this polynomial is called the Burnell-Chaundy polynomial. So we will work in a differential field. So many of the results were developed for specific choices of coefficients, analytic, formal power series, but we are working in the setup of differential algebra with a differential field, with the field of constants, C algebraically closed, and of characteristics 0. Well, an easy example to set up the idea. So given this order 2 Schrodinger operator, then there's another one, A, of order 3 that commutes with it, and both satisfy this this equation. So this would be the Burnell-Choudhury polynomial, and it defines the spectral curve for this pair. These two operators, their orders are prime, 2 and 3. So it's a rank 1 pair. But there's another example, a famous example posted by Dismier, where you have an order 4 operator and an order 6. Obviously, the orders are not prime. They have a common factor 2, but still they will satisfy the same Burnell-Choudhury polynomial, and we will say later why is this happening. So let's stay with Schrodinger operators for a while, because this is where we have the setup better developed and where we have some algorithms, and from here we want to continue. So using a result by Ken Goodyear, we can establish these equivalences. So if we start with Schrodinger operator and assume it is algebro-geometric, then we can prove that the centralizer is determined by this operator LS and another operator A of even order. So, and these two, and by the Burnell-Choudhury theorem, there exists a polynomial Fs, which is satisfied by these two operators. And these two conditions are also equivalents for the potential satisfying one of the KdV equations of the KdV hierarchy. If one goes to the, when I saw this for the first time, then one stays with the usual ways they compute them in mathematical physics. There are some recursion relations to obtain these polynomials, differential polynomials of the KdV hierarchy, and some recursive relations to obtain the differential operators that would commute with a given Schrodinger operator. But if you go to the computer and try to do it yourself, you realize that these conditions, the KdV hierarchy, are just conditions for the existence of a commuting operator fixing one order. And this is exactly what you get. So that's why all of this is equivalent. These are the necessary and sufficient conditions you have to satisfy to be the generator of the partner of the Schrodinger operator in the centralizer. We check all these families of examples, and these are proven to be a dense set inside all the solutions of the KdV hierarchy. And when you talk about solutions of the one of the KdV equations, is a KdV equation of all the possible linear combinations you can do with them using some constants. So determining which equation a potential is satisfying is determining the constants together with the differential operator that will commute with a given Schrodinger operator. So the first thing to make this effective that we did is to develop an algorithm to given a potential, and then obtain the set of constants that will ensure that this an operator of a certain order 2s+1 satisfies commutes with your Schrodinger operator, which is equivalent to the potential satisfying a certain KdV equation. Well, so this was one first step towards making all this construction effective. The second, the next part is having the polynomial defining the spectral curve. So to compute the spectral curve, we will use differential resultants. They are the natural generalization of the algebraic resultant of two univariate polynomials to the non-commutative case. So the differential resultant of two differential operators is the determinant of a Sylvester matrix from an extended system of the two initial operators, and is a condition on the coefficients that guarantees that they have a common solution. So if we go back to the previous examples, the differential resultant of the operators L minus lambda, A minus mu, gives you back the Burnham-Chaudhuri polynomial. But is raised to a power, and this power is the rank, the GCD of the orders. And is a theorem of Emma Previato, the ones that ensures that the differential resultant of two operators, P minus lambda, Q minus mu, has constant coefficients. To start with, what you know is that you have a polynomial in lambda mu. You have eliminated the derivation, but in principle, it will have coefficients in K. And it's this theorem of Emma Previato using the commutativity of P and Q that guarantees that it has constant coefficients. So the situation so far would be that we start with an algebro-geometric Schrodinger operator, and we determine its centralizer. We can compute this other operator of even order commuting with L. And we can compute the Burnham-Chaudhuri polynomial that LS and A2s+1 satisfy using differential resultants. So we have the defining polynomial of the spectral curve. This here is an example with this Rosen-Morse potential. The differential resultant of L1 minus lambda, A3 minus mu would be the determinant of this matrix. And you can observe that the coefficients are left constant after this computation. So the process is, given a potential, we will determine the level, the KdV equation that it satisfies, which means that we will determine the constants that are needed to construct a commuting operator with the given Schrodinger operator, and using this partner, the unique one generating the centralizer, then we get the Burnham-Chaudhuri polynomial of the spectral curve. Well, so I have all the ingredients to tell you what is the factorization problem we want to solve. If we pay attention to this differential resultant, P minus lambda, Q minus mu, the result is an algebraic polynomial in lambda mu, but of course, is not identically zero. So, so the GCD in this coefficient ring of these two operators is 1. They don't have a common factor. We cannot use this to obtain a factor of them. But since the differential resultant is a condition, so we wanted to see where can we guarantee that we can compute a common factor. So we are looking at this other field, assuming that F is irreducible, then we can consider these domains, C lambda mu over the ideal generated by F, and K lambda mu over the ideal generated by F, and their fraction fields, and with coefficients in K gamma, this fraction field, then we can guarantee that P minus lambda and Q minus mu have a common factor, because there the differential resultant would be 0. So the situation now is for a Schrödinger operator is we have the centralizer, we have the spectral curve, and then we can consider coefficient field K of gamma S, and with coefficients in this fraction field, then this is the factorization problem we want to solve, to compute a factor of Ls minus lambda. We are going to compute the common factor of Ls minus lambda A2S plus 1 minus mu. So we will be working in this field. The other option would be to take specialized lambda. Instead of a parameter lambda, take a lambda 0. But we want to work with a variable, an algebraic variable lambda. And that's why we are making this construction, because we want the ideology of drag, where the solutions are expressed in terms of the parameter, the spectral parameter. So looking at this field, the first thing we obtain is that the field of constants is C gamma S, but this is not an algebraically closed field. So for some of the tools one would normally use for factorization or for Picard-Ratio, we have to extend these results. Well, so to compute the factor of operators P minus lambda and Q minus mu, we can use sub-resultants, and the GCD, if the GCD is of order R, then it can be computed with the R sub-resultant. So in the case of the Schrödinger operator, Ls minus lambda, the GCD with A2S plus 1 minus mu is given by the first sub-resultant. So it's an order 1 operator, and with a submatrix of the previous Sylvester matrix, then taking appropriate determinants, we obtain the coefficients of this common factor. In fact, the factorization algorithm would be the next one. So given a potential, given a Schrödinger operator, and the constants that tell you which one is the KdV equation, how is the centralizer, then the algorithm returns the equation of the spectral curve and the common factor, monic common factor of Ls minus lambda A2S minus mu. The factor, of course, in this coefficient field that I told you we are using from now on. So the first step is to define A2S plus 1. Then we can compute the Urlan-Chaudy polynomial with the resultant. Then compute the sub-resultant. And we are going to call phi s minus the quotient of the coefficients of this third order operator, and return derivative minus phi s. Well, so once we have this first order right factor, then we can define the notion of a spectral Picard-Ratio. And the definition would be quite similar to the one you would have for the classical Picard-Ratio, but of course the main difference is that the fields are not constant field is not algebraically closed. So we will say that a differential field extension of this field K gamma S is a spectral Picard-Vecchio extension over the curve gamma S of the equation given by the Schrödinger operator if is a differential field extension generated by a fundamental set of solutions of Ls minus lambda phi equal to 0, and that this extension has the same field of constant as K gamma S. So this extension has the field of constant C gamma S. Well, so this is the definition, and what we did is show that this spectral Picard-Vecchio extension exists, and we want to make it also constructive. Okay, but I'm a bit short on time, but I think I can run a bit over this part. So from the right factor phi s, in fact, we can have two right factors depending on if we take mu we take a2s plus 1 minus mu or plus mu, which can be done because the spectral curve has mu square in the polynomial. So with this phi plus and phi minus, we have two differential relations that define non-zero solutions of the Schrödinger spectral problem. But these solutions, their product turns to be inside the field K gamma S. So in fact, the extension given by these two solutions is just the extension given by one of them. So this extension of K gamma S by psi gamma S is a Liouvillean extension that always exists and is actually the spectral Picard-Vecchio extension over the curve of our given spectral problem. Using results of Manuel Bronstein, we can prove that this the solution defined by this differential relation is a transcendental element over K gamma S, and they have the same field of constants. So this is the spectral Picard-Vecchio extension is always a Liouvillean extension. Then if we compare with classical Picard-Vecchio, we can recover classical Picard-Vecchio for a Schrödinger operator, and instead of lambda, an algebraic parameter, we can specialize and take lambda 0. And we can do this for every point of the spectral curve. Then we will have a factor that is partial minus a phi 0, and this phi 0 is obtained specializing the previous factor with phi s. And this way we can prove that the spectral problem in the specialized case has always a Liouvillean solution where the field of constants is C, which in this case was assumed to be algebraically closed. So the situation is that the spectral Picard-Vecchio fields specialize correctly to the classical Picard-Vecchio field for all but a finite number of points, which are the branch points of the spectral curve. And I wanted to mention too that for us it was very important to consider the one parameter form of the curve when it's possible, which is easier in the rational case, rational spectral curves. And in this case, if we replace lambda and mu by the parametrization of the curve.
Sonia, I'm sorry to interrupt you, but you have 0 minutes left. So you should.
Yes. Yes, I will summarize.
Yeah.
I will summarize. Give me 1 minute.
Yes, yes.
So just to say that, yes, we proved the existence of the spectral pre-Cartesian extension, but we want to compute them. We want to compute this Liouvillean solution. The differential relation, it tells you, it defines the solution, but you cannot compute it like that. So, but if you parameterize, if you use the parametrization of the curve, then the Liouvillean extension sorry. Now, then the coefficient field is now k of tau, the parameter of the curve, and the field of constant is c of tau. So then you can, the advantages that you have is that when the potential is a monovian over this differential field, then you can use the integration, symbolic integration result of Manuel Bronstein and others, and compute the Liouvillean solution given by this differential relation. For example, you can go to Maple, and this will be computed immediately. And well, so I will stop here just to say that we are extending these results to other rank 1 cases, like differential operators of prime order that are algebro-geometric, and also to rank greater than 1, where things are much more difficult because you don't have a Liouvillean extension to start. So I will leave it here. Thank you very much.
Thank you. So maybe you can keep this for a while. So are there any questions for Sonia? We have Carlos.
Yes, thank you, Sonia, for your very nice talk. I just had a very quick question. I'm wondering if this spectral Picard-Becher theory is related in any way to the parameterized Picard-Becher theory of Cassidy and Singer. If there's any connection there.
Well, in the case of rational spectral curves, where this last part that I was trying to rush over, where you can see that the parametrization of the curve, and now your the coefficient field, which is the extension, the field extension of the spectral curve, but now with the c of the k of tau, and field of constant c of tau, then we believe that there's a connection there. Well, is one of these topics that we didn't get into so far yet, but we were looking at the paper of Cassidy Singer, even some of your papers, and we believe that there is some connection there. And we, as you could see, we didn't say anything of differential Galois group, because for the spectral Picard-Bezier extension, there's no notion like that. You will have to make one, and it doesn't seem very easy to define. But if you consider the parameterized case, the one parameter form, and the parameterized Picard-Bezier, maybe the results there can help.
We have one more question, Carlos.
Yeah, so I guess you're using this resultants and sub-resultants that were defined by Chardin, kind of this is the determinant of metric. Well, these resultants, they have factorization formulas in roots in the algebraic case, and I wonder if in the differential case, there is an analog of that.
Factorization formulas, you mean?
Like Poisson formula, or you have a formula like the roots of 1 of f minus the root of g, and then you multiply all of them. And I wonder if in the differential case, there is an analog of that.
Well, in this, there's some Poisson formulas.
Okay.
that would be written in terms of the Wronskians.
Okay, okay. Yeah, I would have imagined that.
Yeah, and in fact, that's what we use to prove some like the result of Emma Previato. We gave a different proof using these Poisson formulas. But then, if you look at differential resultants for differential polynomials, there is where it makes sense. It makes more sense to have these factorization formulas that you are thinking of in the algebraic case.
Yeah.
That is a more general case.
Yeah. Well,
okay, I have to stop you now, and we go to the next lecture, and we'll have half an hour later at the very end.